Yes, here we are again. It's the physics video lecture. Physics 4B video lecture 5. So I have a few demo objects here today. As always though, it's one take, no edit. So wish me luck on this stuff working out. What we're talking about is heat transfer mechanisms. And I decided to come back and show you some demonstrations, because there's really interesting phenomenology here. We want to see some stuff and not just write down formulas. So the heat transfer mechanisms are the way that thermal energy gets from one system to another. And the first thing to remind ourselves is that, I like this cartoon here, when we have a higher and lower temperature object, the energy flows from the higher temperature to the lower temperature object. And the mechanisms for that are threefold. The first one is conduction. So we had a formula. This I represents power, energy per time. And we had minus K A dt dx. And the idea was, here along this x-axis, maybe we have some object with a thickness dx. In other words, you can actually do this for finite increments as well. So I'll write 4 magnitude is just K A delta t over delta x, where one's the thickness. You know, we've got a cross-sectional area here, and we've got higher temperature on one side than the other. Now, if the higher temperature is on the left, then you've got the gradient being negative, and therefore the negative sign turns the whole thing into a positive. So we talked about that last time. I have a couple of values. I could give you some values for this conductivity. The first thing maybe we should do is evaluate what the dimensions are of K. Because here we have watts, here we have area, here we have degrees, here we have length. So actually area over length is a length. So we have watts per meter per degree Celsius. So let's see if we can write that down. Watts per meter per degree Celsius. And again, this is always a good exercise to find the units of something. So the left side here is in power, so that's watts. And then an area over a length is a length. So dividing by that, we get per meter, and then the difference in temperature, degrees Celsius. So that's what these values for K are. And I have a couple here that I'm going to go ahead and put down as a table. So we have K in watts per meter degree Celsius. And I'll just list copper, iron, glass, water, wood, and air. This is actually a good list. Okay, so we have, in case you can't read that, copper, iron, glass, water, wood, and air. And what do we have for the numbers? The copper, 397, the iron, 79.5, the glass 0.8, the water 0.6, the wood 0.08, and the air 0.023. So numerical values are good for comparison purposes. And what we see here is that copper is a very good thermal conductor. We go all the way down through here. Iron, not so much. But then we get into glass, water, wood, air, is a very little, and we say they're insulators. For our purposes, we can think of them as either poor conductors or good insulators. So that's one thing to remember here: poor conductor, good insulator, and air has the very least thermal conductivity in this list. So that'll play a role in a moment. Okay, good. And I assigned an interesting problem for this, and it's just good to be aware of this here. The demonstration that I always show students is that we have, first of all, we've got the flame and the aluminum rod, and the idea is you heat it up here. If you held on at this end long enough, it would actually get warm because, of course, the thermal conductivity, the heat along the rod. Okay. So we've got the flame. This thing is hot. And there's your demonstration. This is for the purposes of drawing a picture. We wrap this thing, see it's already pretty warm here. We wrap this thing with paper and it kind of looks like a roasted marshmallow. The fact is you can roast this paper without it burning. Don't go too crazy on it. On the other hand, and that's because it's wrapped tightly. So actually heat is just conducted right through the paper to the aluminum rod. If you pull a little bit of paper away, of course, it burns immediately. Okay, you got a flame. So that gives you a way to boil water in a paper cup. This is something you guys can try at home. I'm not going to do it here. So this is a demo idea, demonstration idea. Don't get hurt. But if you have a safe flame, you've got a paper cup, and the reason you can boil water in here, let's use another color. So you've got some water in here. You do a very thin layer, the flame here. You've got your flame. The reason this works is the water will never be hotter than 100 degrees Celsius, and the paper layer is so thin that heat passes through that paper. Paper is essentially not getting that hot, not hot enough to burn. Okay, that's the reason it doesn't burn when it's right up against the aluminum. Whereas if you expose it to air, and then it can reach its high temperature. So combustion temperatures are involved here. So boil water in a paper cup if you want to see if you can do that. Okay, so that's a heat conduction idea. Okay, yes, so I'm going to stay on this board here. I can swing the camera up for both boards in a minute, but right now we're just working with this one. So that's heat transfer by conduction. That's number one here. The second example, and there are only 3 heat transfer mechanisms. The second type is referred to as convection. And convection refers to the fluid flow. So heat is transferred by a fluid flow. That fluid can be a gas like air, or it can be a liquid like water. There are interesting demonstrations of this, but I'm just going to do this brief one. This is a very hot flame, and I cannot get too close this way. I can bring my finger in this close to the side, my knuckle, what have you, and there's no danger. And the reason for that is that there's a strong airflow being generated by this heat blasting out here. So there's an air current that's drawing in cooler air from below, first of all. And second of all, the air itself is an insulator or a poor conductor, so you can get pretty close to the heat source. The reason you can't go this way is that then that superheated air is blasting you directly, and it's very hot. So that airflow is what we're talking about here. So let me just illustrate it in the following way. Suppose we have a candle Okay, and then we have a flame here. Mix up some colors for our flame, multicolored flame, okay? So you've got a candle and a flame. What happens is the air is heated, density changes, the heated air rises. So we actually get an air current, a flow like this, and you'll get a smooth flow. In fluid mechanics, you may have learned though that smooth flow will eventually turn, or also called the laminar flow, will turn into a turbulent flow. You can't see the turbulence while the candle's burning. All you have to do is snuff the candle though, and then you have that smoke that's rising, and that smoke that's rising is showing you the fluid flow. And what happens is after you snuff the candle, the smoke dissipates up here. Okay, so that is a heat transfer by fluid flow, and convection refers to that. Now another example, so this is one example. Another important one that ties into the conduction is just the idea if you have a wall here. Okay, so this is a wall, and there's air in between. So let's call this the wall. And then we'll have air in here, and there's of course air outside and inside, but let's say that this is the higher temperature, say it's summer, and the cooler temperature. So this is outside and this is inside, say your house. Then you could think, well, this air gap here is a great insulator. But if you've seen any construction before, you may know that they actually stuff fiberglass insulation between the wall. You may have wondered why. Don't I have a nice air gap here that's going to insulate? What's going to happen though, you've got higher temperature, lower temperature, the heat's trying to flow through this wall. The air is a good insulator, so the heat transfer is small, but what's going to happen with this temperature difference is air currents, called convection currents, actual circulation is going to occur inside the wall. Okay, you're going to get these circulating currents, and they will actually set up in such a manner as to carry the heat from one side to the other more efficiently. So those are called convection currents. So I'll just write here convection currents, convection rolls inside the wall. And if you stuff that kind of fiberglass insulation in the walls, that interrupts the currents, or you could say it makes it impossible for them to form, okay, because there's a network of small air spaces instead. So that's the reason for putting insulation in the wall, where you'd say the air itself is a good insulator. Good. Transfer heat. I'll just write carry heat. Okay, so that's the second type of heat transfer. The third one, I want to first do a demonstration, and then I'll discuss the technical points. So the demonstration is with a very bright light on this side that I'm going to plug in, reflect the light over to this reflector here, and we have matches, and my goal is to ignite the matches from a distance, across the distance length of the table. Yeah, like I said, wish me luck. Let me check the screen here. Okay, everything's on camera. I have to line them up and hope for the best. Okay, put on your welder's glasses. Okay, there we go. Oh, that didn't take long at all. Okay. I was about to make excuses. Yes, you saw it here first. there was clearly some heat transfer because we just ignited those matches right here. They'll now blow out. And this was just a very bright light bulb here. So what about these reflectors? They are parabolic reflectors. They have the property of, if you put a light in the focal point, it sends out parallel rays. And if you bring in parallel rays on this side, they're focused to the focal point, which is where the matches were. Boom, they ignite. So that's nice to have that work. So what type of heat transfer is that? That's heat transfer by radiation. So here, radiation. And when we say radiation, we mean light. Well, it looks like we have light there. It's electromagnetic radiation. Only at the very end of this semester will we possibly get there, and the next semester you get more about that. You know, the bulk of this semester is electricity and magnetism, so we will pretty much just get to there. So the radiation, that's electromagnetic radiation. Radiation. That is light in all of its possible wavelengths. So not just visible light, but all manner of light. Okay, I may go to the full board now. Good, I think that'll work. Yeah, we're looking at heat transfer by electromagnetic radiation. You just saw it. I'll just put that in your notes so you have it. So the demonstration was, we had a very bright light here. So light bulb, and we could say that's a parabolic reflector. And over here we had those are matches. And the matches, as well as the light bulb, are in the focal point of the parabolic reflector. So here we're emitting light in every direction, and it's coming out parallel. And here we're reflecting light, and it's coming in, you know, the parallel rays are being reflected to the focal point, and so you're concentrating the heat. And you got the ignition. Okay, so we lit the matches. So that's a proof of concept. And this is different than conduction and convection. There's air in this room, but this works just as well over a vacuum. So that's how the sun's light and heat makes it to our Earth across the vacuum of outer space. So of course, so this is clearly a very, very important heat transfer mechanism. And I'll just write here, we ignite the matches across the distance of a table. We can do it across the room as well, but right now we're just limited to this amount here. Okay, so there's an interesting law called the Stefan-Boltzmann law. And it's pretty rich, it covers these phenomena, so I'm going to write it down and discuss it. Stefan-Boltzmann. And what it is describing is the power radiated by an object simply based on its temperature. Okay. So radiation, power, and when I say the power radiated, so many watts. Okay. Power radiated by an object and all we have to know a couple things, but an object that has a certain temperature with temperature capital T and parentheses in Kelvin. So this is one of those laws where you have to express the temperature in Kelvin. So let's have a look at it. Stefan Boltzmann law. We'll get a good little picture for that as well. So yeah, there's our third mechanism. I think I'll leave that up there. Convection radiation. Remember, it's always from the hotter to the colder. Okay? So let's have a look. So the idea is this: we have some object, and it is any temperature at all. So we're measuring in terms of Kelvin, so this law holds true for everything down to zero Kelvin. Here's our object, we'll make it multicolored, and it is radiating thermal energy in the form of electromagnetic waves. Okay. So it has temperature T. Maybe I'll just put a big T in here. Temperature T. And so the power radiated, we're using the letter P, we'll use the letter P, is going to be equal to, here we go, sigma E A P to the fourth. So I have to define these things here. We'll start with this. This is the area. This is the one that obviously makes sense, because if I double the area of something that's radiating, I expect to get twice the power, right? Which is, that makes sense. This is a natural constant, and this here is called the emissivity. And let me go ahead and write down the Stefan Boltzmann constant first. So I will say area, right? So temperature in Kelvin, area in square meters, those are standard units. This thing here, emissivity, is just a number. We could say 0 less than or equal to E less than or equal to 1. Of course, that looks kind of like a fudge factor, because any number between 0 and 1, however, a perfect emitter is equal to 1, and a perfect reflector is equal to 0. So typically on any problems we solve with using this law, unless they give us a different number, we're just going to call it 1. Okay, so that's no problem at all. E equals 0, perfect reflector, and E equals 1, perfect emitter and a perfect absorber. We could say it's a so-called black body. Okay. Perfect absorb / emit. Okay. So now we have this law here. And the Stefan Boltzmann constant, well, the first thing we have to talk about is what are the units. Okay. So sigma has the units of watts. This is divided by nothing, okay, from there. Divided by meters squared, divided by Kelvin to the fourth. So we have watts, which I'll write out per meter squared Kelvin to the fourth. And the value of this thing, this is nothing to memorize, I have 5.6696. 696 gives you the idea that it's been very carefully measured times 10 to the minus 8. 10 to the minus 8 watts per square meter Kelvin to the fourth. Okay, so far so good. This is how power is emitted from some object. So we have one homework problem. We're going to have a ball of copper or something, and it's a certain size, and then we talk about how much power it emits based on the temperature. And you plug all these things in, and you're going to come out with watts. But you do see it's a very strong temperature dependence. If you double the temperature in Kelvin of some object that's emitting radiation, which is just some hot object, what's 2 to the fourth power? 2, 4, 8, 16. You double the temperature, you're getting 16 times the emitted power. So let me say a couple more things about this. Because here I said absorb and emit. And by the way, get that while you can read it. It's a perfect absorption or emission. So the thing is, this law actually holds just as true for this object there absorbing radiation. So there's actually a net power, there's absorption and emission. So let's go ahead and erase this here. So note, absorb and emit, the same formula. So what you can say is P net is equal to sigma EA, but then you would have T to the fourth minus T0 to the fourth. So this is for emission, but this is for the absorption. If the temperature of the object and the ambient temperature are the same, then this cancels out and you have 0 net emission. If the object's much hotter, you get emission. If the net emission, if the object is much colder, then this minus sign dominates and you get net absorption. And in equilibrium, the absorption, like I just said, equals the emission in thermodynamic and a radiative equilibrium. Good, we consult the clock. Okay, great. So yeah, I'm gonna assign a couple of problems that deal with this. They're actually pretty interesting. And let's see how we want to set that up. I can set the homework problems up right now, and I'll put them all up on the board at the end of the hour as well. So T greater than T0 net emission, T less than T0 net absorption. Okay. Now, an example of this is our Earth and the Sun. I should say one thing before I go on. Using this expression here, or these down here, you can see that a certain type of light will be characterized by a certain temperature. And you're seeing that on light bulbs these days. You go by a light bulb, they'll tell you about the temperature emission, and that's what's being discussed right here. I want to give this example of the sun and Earth. Because, like I said before, the radiation from the sun is definitely coming across empty space, across a vacuum, and this is the law we're talking about. So let's put the sun out here, and we've got the Earth over here, different size, but that's all right, rotating about its axis. And we've got the temperature of the radiation from the sun. We've got the Earth absorbing that, and let's say that's the entire heat source. There's no heated core of the Earth or anything. We're just going to talk about the radiation due to the sun. So the power in, power to Earth is going to be a certain amount, and it's going to be the same amount. So let's have this. The sun's radiation is coming in here, and based on the geometry, it's really just heating a cross section, heating a cross section pi radius of Earth squared. At the same time, if the Earth's temperature is in equilibrium, which we'll just assume right now, then the Earth is radiating away from it the same amount of energy that it's receiving from the sun. Okay? So there's an equilibrium temperature based on this formula of the Earth radiating away the amount of wattage that it receives from the sun. So the question is, how much power does the Earth receive from the sun? Receives it, radiates it away. It's equal to, so the power here is equal to, it's called an intensity, and I was using the letter I for power in a different context. Right now this is an intensity times the cross-sectional area, and this is an intensity called the solar constant, and the area is, let's see, not 4 pi, it's pi radius of Earth squared. Because the Earth is presenting just a cross-section of its area to the sun. Okay. So we have to say, what is the solar constant? The solar constant is refers to the amount of wattage per square meter that the Earth receives. So if you go out on a really sunny day, sun's directly overhead, there's a square meter, then you can say so and so many watts are onto that square meter. Strictly speaking, it's above the atmosphere where there's no absorption due to the atmosphere. So the solar constant can be measured very accurately, 1,340 watts per square meter. So yeah, make sure you recognize that. What we're talking about, it's power per square meter. Go out in the sun and carefully measure it. Go above the atmosphere and carefully measure it, it's even better. And so how much power is the Earth receiving? Well, it's receiving 1,340 watts per square meter times pi radius of Earth squared. Okay. So that's how much it's receiving, and that's also how much it's emitting. So for the emission, we would use this number here. We could ignore the difference one. We can just use this for the emission. Sigma is what it is. E, for the time being, we'll just call it 1. That's actually an important point for the actual accurate number, but for us, we would just set it equal to 1. Here we would take the surface area of the sphere, so 4 pi radius squared, and then temperature to the 4th. Well, the only unknown here would be the temperature, so you would solve for the temperature and you'd find out in Kelvin what the thermodynamic temperature of the Earth is as it radiates away power. So that would be a very basic equilibrium calculation. Good, so we talked about solar constant. these are the things you want to know before you get into any really technical details. Just the basic, these basic formulas. This formula here we have to treat completely as an empirical law. We did not even attempt a theoretical derivation of it, okay? Did not attempt that, so this is empirical law. Okay. So what about our homework problems for this topic here? I had a few. I think I'll consult and set them up for you guys right now. So I have chapter 20, problems 43, 44, and 45. Use of these formulas. I'll leave these formulas up and just use this side of the board to discuss. And I'll put these up on the end of the hour as well. But homework, we have chapter 20, 43, 44, and 45. And I'll just say a word or two about each one. 43 is really just a plug it in problem for this formula here, because we're going to assume 1,000 watts of radiation, and we're going to assume a certain temperature. Got to make sure it's converted to Kelvin, and we're just going to solve for the surface area. So the problem 43, area of heating coils. But everybody's seen a space heater. You plug it in, the heating coils get red hot, they give off heat, and they're actually just an expression of this law here. So it's 1,000 watt, let me check the numbers here. 1,000 watt, kilowatt, 900 degrees Celsius. Make sure you convert to Kelvin, okay? And that's right. So that's a perfect example. Heating coils, 1,000 watts, you plug it in, 1,000 watts. Just let E be equal to 1. You have a temperature there, convert to Kelvin, fourth power, solve for the area amp with heating coils. I'll give another example. So this is the problem. Now you can do the same problem for, say, an old incandescent light bulb, which has a very tiny heating coil. Okay, it doesn't have a heating coil, it has a filament. Same for an incandescent light bulb. We'll just draw one. Okay, there's the shell, and you've got a light bulb here, right? Inside you have this little filament, and you make the same assumptions and say it's a 100 watt bulb. So say it's a 100 watt bulb, and you know the area, because maybe you know the area of this really thin wire, and you're talking about how much, how high is the temperature. So for a space heater, which is this problem, the heating coil is just glow red. That's nowhere near as hot as this incandescent light bulb. It's a very tiny filament, has a tiny area, has a very high temperature. Okay, so there's a difference. Same formula. Okay, what else do we have here? Problem 44. This one's great. So for problem 44, let me go ahead and make a little more room here. I'm sorry, this was 43. This was 43. Problem 44, we're talking about a copper sphere with some radius. And we're going to have to use two formulas. So I'll just point out. So for this copper sphere, we have power equals MC. Here, let me remind you. So say we had a piece of copper and we had Q, all right, dQ equals MC delta T, or dP, okay? So the power is dQ dt is equal to MC d temperature, change of temperature with respect to time. So that's the power being radiated by this copper sphere, and you're going to bring it into connection with the power being radiated in this sense. So this is the change of the heat, right? The heat content expressed as power, and if it's all being radiated according to this formula, you're going to bring these two expressions into connection. So that's a nice problem. And problem 45 I see is the one about the incandescent light. So we've covered all three of these. Good. And all three of these really bring this topic into nice focus. Okay, so we're going to move on. Okay. And in fact, we can segue nicely, because the whole discussion here is heat transfer. And previous to that heat transfer was the idea that it goes from hot to cold. So that's our next continuing discussion. Okay. So heat transfer, still the topic. Transfer of thermal energy. And again, it's this cartoon that I like to put up, just so that we never forget. And this is also one that is fundamental, okay? Nobody's arguing with this one. You have something hot, the energy spreads into something cooler. You would not, for instance, have two objects in contact with each other and have the cold one get even colder and the hot one get even hotter. Okay, that's just never going to happen. So if we want to get a deeper understanding of this direction of energy flow, that's what our next topic is. And I'm going to introduce the word entropy as a measure of disorder. Is a measure of disorder. So the example is nice with the change of phase, of course. So say we have our ice block, and then we add energy, and we get the liquid, and we add some more energy. This is what we did the other day, and then I'll draw a balloon, right? We get the gas. So we got the solid, liquid, gas, okay? And say it was all from the same chunk of water, chunk of ice, then we would say the ice versus the fluid. Actually, I have to say liquid, because gas and liquid are good. So liquid water versus the gas, we would say, well, the ice is the most orderly, so it has the least entropy. Least entropy. The liquid's intermediate, and the gas has the most entropy. But it's a quantity that we have to be talking about the same amount. So if this were, say, a kilogram, 1 kilogram, 1 kilogram, 1 kilogram. So a kilogram of ice is a little block of ice. A kilogram of water is a liter. In fact, you know, the ice is a little more, has a little slightly larger volume. And a kilogram of air is just a bit less than a cubic meter. So you can keep them all in view. So a measure of this disorder, as we're calling it, is called entropy. And the way the entropy changes is with the addition or taking out some thermal energy. Well, that's one way it can change. Okay? So we're going to say change of entropy is equal to delta Q over T, temperature in Kelvin. So the units apparently, so the units of this delta S, and we're always actually going to keep the delta there, or the ds. So yeah, what are the units? Joules per Kelvin. Since we know that temperature itself is a measure of energy, in that sense, you could also have entropy as a dimensionless quantity. But we'll keep it with these dimensions here, joules per Kelvin. So that's our entropy. And what I want to bring this into contact with is this law of higher to lower temperature, okay, energy flow. We kind of already talked about it with the heat transfer due to collisions when I was talking about collision, you know, in a solid here. Because the rapidly moving molecules are more disordered than the locked into place molecules. And if you bring these two objects into contact, then the moving ones kick the immobile ones and get them moving as well. So that motion transmits. And right, the thermal energy looked at microscopically is motion. So that's a consistent idea. Let's pursue this a little more. I'll give you a couple of examples. We can also, I'm leaving out some technical details by the way, but we can also write this as ds equals dq over t. And in both cases, ds is greater than 0 if energy flows into a substance, and ds is less than 0 if energy flows out. Okay, so we'll just take that as a convention. And we're thinking of energy flowing into an object. This picture is really nice in the sense that we have energy flowing out of TH and the same amount flowing into TC. Okay, we're going to analyze that in a moment. Let me first give some examples. Two examples. So suppose we melt ice from 0 degrees Celsius to 0 degrees Celsius. We just slowly put the heat in, the ice melts, temperature stays the same. So ice melting at 0 degrees Celsius, which we know is 273 Kelvin. Is there a change of entropy? Certainly, right? The ice is locked in place, the fluid is fluid. The molecules can move around more. Here they're more immobile. What's the change of entropy? So here the delta S is equal to mass latent heat of fusion. Remember, that's our Q. Right? That's our Q, mass times latent heat of fusion, divided by T, and T has to be 273 Kelvin. And if you plug in, say, a kilogram and latent heat of fusion of water divided by 273, you'll get some number, okay? Positive, because that heat flowed into the water, into the ice, turned it into water, liquid. The other example, so this is one. The other example I'll say is water heated from T1 to T2. And let's just say those are two numbers between 0 and 100, okay? So no vaporization involved. Then the delta S would be the integral of this dq over t from T1 to T2, okay? Integral, of course, is just the summation of all of these expressions, but we have an expression for that. We're going to have the integral T1 to T2 of mc dt, that's our mc delta t, with specific heat, divided by t. And in this case, we've got the mass of water, specific heat of water. The integral dt over t is the natural logarithm from the upper boundary to the lower boundary, so that's just natural logarithm T2 divided by T1. And so, yeah, that would also be this entropy. Good. MC delta T over T. So those are examples. And once again, consult the clock. Good, perfect timing. Now I want to use the entropy definition and these laws here. I'm actually going to leave these up here, and I'll erase this, to discuss this scenario right here. So what we're going to do is take this idea of a system and imagine we take the hot and the cold object and we lock them in a cooler. We lock them in an isolated, insulated box. So consider this isolated system, and it's the same cartoon, TH, TC, it's TC, heat flows from one to the other. But the idea now is I'm just going to put them in a box. Okay? That's what it means to be isolated. Like you put two things in a cooler, put the lid down, and nothing gets in, nothing gets out. So there's our isolated system, and we want to calculate the total entropy change. Calculate total change of entropy. And this is just the very simple version of this, but here we go. We would say delta S total is going to be delta S from the hot one here plus delta S from the cold one. But it's the same amount of heat. It just left one and entered the other. So here's what we get. We get, because the energy is leaving TH, we get minus Q over TH, and because it's entering TC, we get plus Q over TC. And this Q is a, I could put absolute value signs around it, but I won't, right? This Q is a positive quantum of energy, so and so many joules. Now let's just factor out the Q, and we've got 1 over TC minus 1 over TH, get a common denominator, and then we have TH minus TC. So this is the total entropy change for an isolated system. And what we can see is, because these are Kelvin degrees, right, Kelvin temperature, this is always positive, right? The higher temperature minus lower temperature. So an isolated system, this is always greater than or equal to 0. So the change of entropy of an isolated system always being greater than or equal to 0 is equivalent to the demand and or the fact of nature that energy flows from the hot to the cold. Okay? So this is actually an expression of a fundamental law called the second law of thermodynamics. In the Clausius formulation, you'll find it in your book. You may be wondering, why the second law when we haven't talked about the first law yet? But that's just the way we're doing it. Don't worry. So this is always greater than or equal to 0. So let's go ahead and put this in words. The entropy of an isolated system increases. At best, it stays the same. Okay. That's the second law of thermo. Very, very important. And important for us is it's as fundamental as energy flowing from hot to cold. So that's what I'm going to leave us with. And this is, like I said, this is the really elementary discussion of entropy, but it should be completely transparent and make complete sense to you. So that's why I did it this way first. We will pick up with this next time and eventually move into heat engines. So until then, see you guys later.